here. Okay, so for today's lecture, we're going to be talking about asynchronous computation within the context of Spark and Scala, and the ways in which that can simplify programming while at the same time enhancing performance, lowering the number of threads that have to be created, allowing for minimization of the number of round-trip messages required to external servers performing tasks, and generally allowing for more scalable and transparent applications. Now, the primary mechanism we're going to be focusing on for that is something called a future, and it turns out that that this is quite central to how asynchronous operations are handled within Spark. There's a variant of it, which is the most common mechanism for using it, called a future action, which we might be able to look at the very end, and which has some extra features like being cancelable, etc. But for today's lecture, I'm going to be having a marked departure from past lectures, in the sense that I'm not going to be using Zeppelin for this, because one of the things I found out was that Zeppelin does not play really nicely with the asynchronous mechanisms we're going to be exploring. It's not nearly as helpful to explore within Zeppelin as it is actually from the plain old Spark shell or Scala shell. Okay, so for today's lecture, rather than operating in Zeppelin, what we're going to be doing is we're going to be actually using the Scala or Spark shell. Now, if you have the Scala or Spark shell already installed, you can use that, okay? Otherwise, I'm going to give you some instructions about something you can do whilst I'm sort of covering some basics conceptually of motivation and where futures fit in. You can start to download a Dockerized version of the Scala shell, okay? And that will allow you to, by the time we get around to doing some practical examples, hopefully you'll have it present. It is a large download, so you should get going soon. So I'm going to switch over to screen sharing here. There we go. And I'd like you to go to, if you already have Scala or the Spark shell installed and you want to fire that up, that's great. Otherwise, I'd like you to download and run a Docker image. And the way in which you're going to download it is you're going to say docker pull hcburger/scala-sbt. One of the things I would have loved to cover in this class, and probably given one more class, I would have done it. I may secretly record one more class and broadcast it to you folks. Or maybe we'll have a reunion. It's the SBT shell. So this is the Scala build tool. And it's an extremely useful, powerful way of operating with Scala in a way that allows for compilation, management of dependencies, etc. And what we're pulling down is a Docker image that supports that, but it also supports the Scala shell, which is really what we're using here. We're not going to be today going into SBT as a tool, but I'd like you to Docker pull this. Now, this is a pretty big Docker image. It gets to hundreds of megabytes. So pull it early, and it should start to download. Make sure you're connected for the web for this and for other things we're coming up with. So if you do a Docker pull, then what you're going to do after that's running is you're going to run it interactively. This is the interactive option with Scala. You can be running this Scala SBT package here. And what you're going to want to do is to make sure you enable network connectivity whilst in the shell, because we're going to have some examples which are going to depend on that over the course of today's class. So I will come back to this once people have downloaded it. But set it downloading now, and it will probably take a little bit of time, okay? So the key thing right now is to start this Docker pull. Okay. So within today's lecture, we're going to be talking about mechanisms for asynchronous computation. These are mechanisms which support concurrency a single core. But in general, as we've moved increasingly to parallel systems with multi-cores on a given machine, given even laptop, and then even on tablets, and then distributed computation, a lot of our interest in concurrency is so we can take advantage of parallelism. But you should realize it's not the same thing. We may have other reasons for being interested in concurrency other than parallelism. So concurrency is possible in general if we have A and B, task A, task B. If B depends directly on the result of A, we're not going to be able to execute them concurrently. B can't start until A is done, right? B depends upon A's result, so it can't fire up until A is done. But if B doesn't depend on A's result, maybe both depend on some input, and both need to be finished before you can go on, but B doesn't have to wait for A and A doesn't have to wait for B, then they can execute concurrently. They can execute in an overlapped way, and ideally in a parallel way. Now, this raises an issue with traditional programming models. I think most people in the room grew up with a model of computation and a model of programming where we do things in sequence. We say, do this, and then do that, and do this other thing, etc. We do A, B, C, D, and we finish A, and then we go on to B, and go on to C, etc. We have a set of tasks that we undertake one by one. And maybe we don't just do them once, we do them several times, so we have a loop which goes between them, go with A, B, C, A, B, C, A, B, C, or something like that. But there's still this sequential nature of it. A goes before B, or B goes before A, and they're not running at the same time in our programming abstractions. So we're used to thinking about programming traditionally in a very sequential way. But today, many frameworks, from simulation systems like AnyLogic to systems for programming with GUIs, right? With event-driven programming, you click on a button and it invokes some code, to frameworks like Node.js for asynchronous JavaScript and handling a rich UI experience, to reactive frameworks. They've gone beyond this framework for very good reasons. And one of them is we want to avoid blocking, right? We want to avoid holding up a thread. If A goes and then B goes and then C goes, maybe if B doesn't depend on A, why are we holding up starting B until A is done? We're blocking getting to B while we're waiting for A, especially if A involves I/O, involves input/output. If it involves just some long operation that doesn't chew up the processor, it just involves going out and getting some information over the web. Why hold up B for that, right? The processor is sitting there doing nothing. We might as well get on to doing B. So one big recognition here is that with traditional models of programming, we're doing a lot of blocking. We're waiting for things we don't need to wait for, because actually they don't require a lot of computation. They require awaiting user input or awaiting I/O from some source. Now, in asynchronous computation, we're going to be turning that on its head, and we're going to be undertaking things. When things are done, we'll react to them. Just like when the user presses that button, we react to it, right? When the message comes back, or when our request comes back from the web, we'll be notified and we'll handle that request. But we don't have to sit there waiting for it. So futures are a monadic way of capturing future values that are very popular. They're very central to constructs in actor-based programming languages, which are a popular way of dealing with asynchronous, and which Scala supports with the Akka model, et cetera, or the Akka framework. And they're monadic in character. They allow us to capture values, but capture metadata about values, like how it is to be computed, okay? Here, we're going to be capturing these future values, these sort of promises of having a value, a deferred value. And then we can go on to successive stages of processing when the value is available. Whenever it becomes available, we'll do the next things. And I want to contrapose this to something many of you may have used, which are callback mechanisms. If you've programmed in operating systems at a low level, if you've put in place mechanisms for dealing with socket level I/O, for example, you may have used callbacks. These are mechanisms that basically say, hey, when this is done, call me back explicitly. You pass in a pointer to a function or something. You say, hey, call this when you're done. And it turns out futures are a much, much, much cleaner way of sort of capturing similar functionality. So a couple of motivations for asynchronous abstractions. When are they particularly attractive? Well, if we have very long duration, but low compute effort operations, the classic example here is I/O. We're waiting for storage. We're waiting for a disk to get around to finding some data, or we're waiting for some data to come back from the web, or we're waiting for a database query to take place. We're waiting for something that requires very little computational effort. The processor is literally sitting idle during that time by default. We could get it to better use if we could handle something else concurrently. Another example is, where you have the environment. A lot of your things are triggered based on the environment. So you have a system in a car that has to respond to environmental stimuli, so when something comes up unexpectedly, or you have a system that handles messages from the external world, email messages arriving or Ethica data arriving, and you want to do something with it at that time. You want to display it or what have you. Here, we have an environment, and it's, rather than just being able to say, do A, B, C, we're just waiting for the environment to say, hey, something has happened, and then we'll act on it, right? We can't pre-schedule this. And it's kind of a crude thing to do, to just loop and say, is there anything there yet? Is there anything there yet? Is there anything there yet? Do you have anything yet? We have better things to do in life than to constantly poll, constantly ask. And It's much more natural to have an event-driven system where it notifies us when something's available and we'll act on it, rather than constantly checking and spinning our wheels. When you have limited dependencies between operations, I emphasize limited. The obvious example, the counterposed example, is if you have several operations and each depends upon the previous one, or all the previous ones, we have really tight dependencies. And there, we're not going to gain much benefit from asynchronous operations. I mean, we might as well just execute them sequentially. There's not a lot of benefit in knowing when the last one finished executed so we can go on to the next, because we can't go on to the next until it finishes in most cases, and we might as well just wait for it to finish and go on and fall through directly, which is what synchronous mechanisms do, traditional sequential. If we have many independent operations, like we have a broad set of tasks, if we're doing load balancing in a system with many tasks, we have many different things to do, a whole pool of different things to do, and they're fairly independent. You know, we could do A, we could do B, we could do C, we could do Z, we could do X, Y. You know, all these different things. We just want to handle these different things in the pool without a lot of connections between them. It doesn't make a lot of sense to do this in a very synchronous fashion. We fire them up, we get notified when they're done, and we can take the results and maybe put them somewhere, or record it in our log, but they're fairly independent. Another thing is, if you have a request, you'd like to be able to fire up, but then cancel based on something, like the user clicks cancel or something. If you just have A goes on to B and goes on to C, and A starts B, and then you decide, oh, well, I don't want B to be executing. Well, it's already in the middle of executing it. You're no longer after A. There's not a lot of opportunities to cancel B and come back to C. It's a hard thing to do. Whereas if what happens is B is fired up and we're just waiting for a message when B is done, we could say, hey, go cancel you, because we can go on and do other work while B is executing. And one of the pieces of work, we could tell it, stop executing. You're not needed anymore. And in fact, this is what we get in Spark. We get a cancel that can cancel futures. We could say, hey, don't bother about that. I don't need it anymore. You know, don't go on execute any further stages of that. I'm done. I've got everything I need. I don't need it. And then finally, and this is quite central to this course's kind of motivation, sometimes it's just much more elegant to respond to operations in an asynchronous fashion. And I want to highlight, these are sort of software engineering benefits. A lot of these have to do with additional types of benefits, performance, scalability, et cetera. Here, we have very nice programming models that have been evolved to handle asynchronous models of computation. One of them is the event-driven handling mechanisms that you see in a lot of GUI programming systems, right? You are invoked when this button is clicked, or when this dropdown is changed, or you're invoked when a link is clicked. These are common abstractions that make programming GUIs much nicer than when I started my life programming GUIs, where basically we were writing event loops. We were writing this loop. It was the WinProc, and it would loop around and basically check, okay, what's in the queue, and handle it. And now we get invoked when these things happen. And you can imagine in any logic, for those of you, many in the room are familiar with any logic. In any logic, we have these event handlers, right, that go off when you transition state, or when an event fires, right? I mean, it's even called an event object. It fires, or when the user clicks a button. We can also handle things like that. When the whole model starts running, when it stops running, when an agent is created, when the agent is destroyed. There's all these different handlers we write for different circumstances. And the rule here is what's called the Hollywood principle sometimes. And it's increasingly the main way of operating in many contexts. And it reflects inversion of control. The Hollywood principle is don't call us, we'll call you. I've mentioned it before. But it's quite central in terms of creating a model which is very natural for event-driven systems. For event-driven systems that are based on user input, there sometimes is not a lot to do until the user gives some further input. So why are we constantly busily checking, has the user given input yet? Have they given it yet? We might as well just be notified and let the processor do more useful things with other programs or what have you. And reactive programming has taken this up very much as a model in a way that originated in the functional community. Reactive programming came out of ideas in functional programming. Indeed, as actor-based systems did, came out of work with Scheme at MIT in the early 70s, and Scheme and at Lisp, and then turned into a whole actor-based way of computation that's very rich. That's one type of thing. Another thing is there's a traditional way within functional languages of capturing asynchronous things called continuation passing style. This is called CPS in short. It's a very elegant way and much more powerful way of capturing things like event-driven programming or like aspects and even things like exception handling. So CPS is a very powerful mechanism, but it's kind of hard for people to think about. You pass around these closures, which basically say this is what to do next. And when you're done with your thing, you pass what your result is to the closure, to this continuation, and it goes on and does its different things. And sometimes you have different continuations. One that's passed in if you get an exception or if something bad happens, and one that's passed in if everything goes well, and you call the appropriate one. It works, but it's not all that nice. And the use of futures allows this what's called the direct style instead, which is very similar in some ways to our traditional way of programming, where we think sequentially, but it supports wonderful concurrency and, by extension, parallelism. So future-based mechanisms are one way of permitting the direct style. Other contexts, like, for example, Dart, it turns out, supports other constructs like having an await construct to allow for similar sort of mechanisms, although in a little bit more of a CPS type fashion, a continuation passing fashion. Okay, so when it comes to Scala futures and Spark futures, we're going to have a set of benefits here that are going to be associated with how we program. It's going to be very natural to sort of define and continue computations while we do other things. And it turns out, in a way I don't have a chance to cover today, and indeed in this class, there's a technique known as future pipelining, which uses futures to minimize the number of round trips to distributed resources where you're requesting work to be done. Okay, so it turns out with actor-based systems and futures in general, you can really lower the number of network round trips required to coordinate a set of distributed computation through this technique known as future pipelining. And part of it is because you can have resources living as futures on external machines, and if they're kind of on the same machine, a lot of work can be done locally that otherwise would require central direction, sort of exchanging messages back and forth with the server. So I don't have time to go into this today, but it's an important feature of futures that can have significant implications for network utilization. Okay, now within Scala, we have really nice support for futures. Turns out that recently this has been extended to Java, so Java 8 completable futures, I believe they're called. We have a somewhat similar model, and not surprising to you, since this is a monad, we have very familiar components here. We have flat map, we have map, we have filter, and these reflect the fact that a future, like other monads, is sort of this package, this container that contains a value. Okay, and we can have a future of type T, and it's kind of a promise for a future value. I have to be careful because the word promise and future is actually used in a more detailed technical sense. I'm using it in a more colloquial way. A future is kind of a deferred value, a promise of a value at some later point. Maybe it's available now, maybe it's only available later. And we can map it, for example, with a function that takes that value to a different type. We get out a future of S. We started with a future of T. We have a function that applies T to S, and we get a future of S. It's like lifting F to the future domain. Or we have a flat map. And you remember flat map is different from map in the sense that it can return a monad. The function can return a monad. And we get out a monad of that sort. We can filter a monad. We get out a future of type T, etc. But it turns out there's a set of other operations as well. We can ask, is it completed or is it still underway? If it is completed, what's its value? If you ask that when it's not completed, you'll get a none. And in general, you will get an option of try of T. Let's take that apart. Why the option on the outside? I've already given you the hint. Why the option on the outside? Because if it's not yet completed, you get none. That's option, right? An option, you either have some or none. None says, hey, it's not there yet. Okay. Why try of T? Why try of T? What's that monad capturing? That it might have what? Yeah, it might have failed. It might not have succeeded. And this will actually wrap up inside of it why it failed, the exception that occurred. Okay. And then we have some additional components which are extremely useful in practice. On complete and on success are two of the most important ones. Sorry, on complete, on success, and on failure here. Incomplete is actually, I think, getting deprecated. It's not encouraged. On success and on failure are key ones. So on success as well, if the thing we're trying to do succeeds, this gets called, and it's a partial function here that can operate on this. And then we can have an on failure, which also takes a partial function and handles the case if it's failed. Okay, we do something if it's failed. We do something if it succeed. Here we're doing something if it completes. And collect can work too also with a partial function. And do you remember what collect does? It's like what two things combined together? Filter. Yeah. Yeah, exactly. It's like a filter and map. So we're filtering out things which are not in the domain, the range of this partial, not in the domain of this partial function. In other words, aren't covered by the partial function. But for those things that are, we're mapping them to something of type U, and we're getting a future of U. Okay, so I'd like to fire up our Scala shell. So now let's go. I've asked you to download that, and I'm going to go back here, and I've actually got mine up already, but I will go and I will go shut it down. Oh no, I don't. Here we go. Okay, so this is what I'm going to be running. Oh, it's being cut off. There we are. It's this guy here. Okay, Docker run minus IT. Da, 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 da. Okay, now, so I'll put it up here on bigger. Oh, sorry. There you go. This is the one you want to run. Okay. Now, when you do this, you should be placed in the Docker container with a root access with administrative access there. Okay, and I'll show you what it looks like in a minute. Again, this is running it interactively. You're on the command line. Inside of that, you are enabling the host sort of level of networking, so you can access the net from within it. And we're naming it Scala, and this refers to the Docker image that we're going to be running. And this will fire up a container that it's going to be running. So do you folks need a bit more time?
Getting an error.
Oh, okay. What error are you getting?
Docker run requires at least one argument.
Yeah.
Even though we've given it a number of arguments.
Yeah, maybe try to remove the net equal host. That's for Linux, not for Mac.
Ah.
Yeah.
Okay. So get rid of the -- net equal host.
Yeah.
Okay. Awesome. That's great. So for Mac, so this is like Linux. This one. For Linux, we'll do this. For Mac, we will do. I think it sounds like it's suffering a Mac attack. Okay, here we go. There. Okay, it worked on yours.
Yeah.
Some Macs. Some Macs. Big Macs. Something like that.
Yeah, the change didn't work for me.
Could you try? Okay, if you're having trouble, could you try just running it with Docker run -it and just this component here? Although you probably want the --rm as well. This guy, and then this final specification of the Docker, the Docker image. Whilst you're doing this, I'm going to do something I meant to do before, which is I'm going to email me the notes so I can know. Okay, why is that out there? Okay. Hey, come on, get back here. Okay. Okay. And here we go. Great. Boom. April 5 lecture notes. What's that? Any luck with that?
Oh, I got it.
Okay. What did the Wade do?
I had missed a space between two.
Between two of the arguments.
Yeah.
Which?
Between Scala and the name of the HC burger. Because it wrapped.
It wrapped.
Window, so I didn't.
Yeah, this should be a space there. So the full thing works now. Wait.
Yes.
Okay, so maybe I need to eliminate the Big Mac. Okay. Okay. Let's. Do we have that working? Who else needs help? Did everyone get it, or the Imans is still truculent? Okay. So what I'm going to do, whilst you're trying to figure that out, so is everyone working except Imans? Okay. Nell, yours is?
Yes, I just hit something that acted funny.
Oh, okay. Okay, so what I'm going to do is I'm going to invoke this same thing, which I've put in a bash thing here. So I'm gonna bash it. Okay. And now I'm in the shell here within it. And if I do ls, I'll see this. What I need you to do within this shell is just do Scala. Okay. Okay. Yeah. So do you want that up still? This one here? You need that? Okay. Yeah, make sure there's spaces between each of these things, including after Scala. And this guy, yeah. I would successfully remove, you know, some of these options just to see, but.
Yeah, it works.
Okay, so what did you have to do?
The name, the darker name is wrong.
Oh, the HC burger?
And yeah, the image name should be some type arrow, something. So I just copy and the correct name.
Great. Okay. Okay. So it's a typo. Okay. Okay. So, ladies and gentlemen, we're going to go in and we're going to put in place some mechanisms here. And for the sake of time, I think what I'm actually going to do is we're going to reduce this a little bit. I'm just going to make this 30 times 1,000 rather than waiting quite as long. So, oh wait, don't do that quite yet. I've got to get you to enter some imports. Here you go. So up front, we're going to import a bunch of things, and just so we have the same set all done up front, I'm going to ask you to import here Scala. Here we go. Scala.concurrent.future. Scala.concurrent.execution context.implicits.global. I'm not sure that one actually is absolutely key to our needs today, but it certainly won't hurt.
It wouldn't work without it.
Okay,
Yeah.
great.
Fantastic.
Okay. That's great. Much appreciated, Dorian. Scala.io.underbar. Scala.io.studin.underbar. Scala.util.underbar. And finally, Scala.util.random.underbar. Sorry. Okay, so I'll go down here. You can see them in bigger type if you want to. So import all of these guys. Okay. Okay, so what we're going to do, we're going to have a couple basic examples, and we're going to build up a little bit towards something a little bit more significant. We're operating here with futures. As time allows, I'm going to get into future actions later, which are Spark specific. So we have futures, and future actions are futures, but they add a bit of functionality associated with, say, canceling a future. Okay. Okay, so the first thing is we're going to create a future, okay? I want all of you to have a good future. So we're going to say my future 1 equals future of 3, okay? This is the most basic future. And you notice it creates this future int. So it's kind of this promise of having an int, or this deferred int, right? Here, if I say my future 1 dot is completed, it'll of course say true because it's right there from the start. And I could naturally ask for its value, for example. And you remember, this is when we ask for its value, we get an option saying whether or not it's there, and then an indication if it succeeded. And of course, it did here, right? We could also do something like this: my future 1 dot for each, okay, for each thing in it. We could do println of that actual value there, and it's going to print out the 3. This is a monad. It contains values, one or more values. In this case, it's just one or zero. Zero not yet having been computed. And here we're printing out what's in that, right? Oh, sorry? It says it's not completed yet. Yeah. Even though you did future of 3.
Yeah.
Yeah, mine said that too, but then when I did is completed, it said true.
Oh, you're saying when you say Nell, when you say it says it's not completed, do you mean when you said this or earlier?
Earlier.
Yeah. Okay. So it may not have computed it at the time immediately, but if you say is completed, is it true now?
Sometimes it probably just doesn't check if it has nothing to do before it returns.
Yeah. Yeah. Exactly.
So it always assumes.
Yeah. Yeah. That's good. Do you think maybe, given that Saskatoon is apparently has the biggest temperature anomaly in the world right now, biggest, coldest, the strongest departure from normal temperatures right now is in Saskatoon. Do you think the machines maybe are running slower? So hopefully they don't freeze though, right? Freeze up. Okay. Okay, so let's do another one. My future, this future is not so bright. Oh, my future 2. Sorry, make it my future 2. There. I'll make my future 1, return it to that state. But I mean my future 2 here. What do you think that's going to return? You'll notice, by the way, Nell, this duplicates the Nell experience here, not completed. Yeah. Okay, so let's ask now. My future 1 dot is completed, and it's going to say true. What do you think we'll get if we ask for its value? Oh, sorry. I'm sorry. I meant to do my future 2. Sorry, folks. My future 2 is completed. Yeah, it's completed. But what do you think if we ask for its value? Yeah, we'll get something. It's there after all, but it contains a failure, right? This is this part of try, right? This is this thing from try here, yeah, right? And so it contains a failure rather than a success. Okay, so things can fail. Things that we want to perform asynchronously, maybe execution on some external machine, maybe it's a long latency access over the web for some information. We're harvesting some information from a website and the website's down. Or we're trying to go to a database and the connection is not possible, and it times out. We get back to failure, right? Okay. So futures can contain that. You'll notice that while it was not completed, it didn't block us from doing things. We could go on and do things, here, and it wasn't blocking. It was asynchronous. It's not. We're not waiting for it to be done before we can go into the next thing in sort of a synchronous fashion, and sense that we're on the same clock, or I'm waiting for this to be done in a sequential way to go on to the next thing. It was operating, in fact, concurrently, and it wasn't computed, and eventually it did compute it, although it was a failure in this case. Okay, so let's explore this some more. Let's do so val my future 1a. Okay, this is just a variant in the one we did earlier. I'm going to do a future of 3, and I'm going to say on success. What does on success do? What is this on success?
Function to call when it's successful.
Yeah, exactly. It's going to, if it's successful, we're going to call something. I think I'm going to do something more interesting. You folks, we have limited time today, and so I'll do something more interesting. I'll say source dot, here we go, source dot from URL. And we're going to say HTTPS : //www.usas.ca. Okay, so this is HTTPS, the secure protocol. I'll give you notice. And then I'm going to say dot make string. Okay, and here actually no. Here we'll actually say on success. We'll actually say, okay, maybe we'll, to get this most general, I'm going to say on complete. How is on complete different than on success? Anyone? Well,
Still run if it fails.
yeah, it'll still run if it fails. And what we're going to say is case success. Okay, of V here. Okay, right. We'll say println. We'll just print out what we're operating on. This is V dot make string. I'm actually ad-libbing a bit here, so I may get myself in trouble, but I'm trying to make it a little bit more interesting. And otherwise, we're going, and so I'll do a semicolon here to indicate this is on the same line here. Case failure of E, print error exception, and we'll say plus E. Okay, there we go. And we're going to need to close this guy, and then close that guy, and then close this one. Okay. There we go. Okay, so what just happened here? Did you notice the delay there for a minute? Watch this. Yeah, it actually delayed it a little bit. Okay. Maybe, well, there's there's a lot there. Maybe to make it kind of nicer, we'll do vk.makestring.size. Okay, there it is. So you'll notice when I first executed it, it said, okay, it returned immediately. And then it printed out this. Whence did this come? What is this? What is this thing? It's the size of the U of S webpage, right? Let's go here and put in place a URL that won't work, right? So USAS foobar. I'm pretty sure that doesn't exist anywhere, right? Okay, so now we got back this message, unknown host exception, right? So it encountered a error, and it's reporting the error. It's reporting that it's an unknown host, and it reported the host that caused the problem. So what we put into place here was a little mechanism. It's an asynchronous mechanism. We've requested this, and whenever it completes, however long it takes, maybe it will take a while, it's asynchronous. Whenever it completes, we'll go on and do one of these two things. This parses the situation where it's successful, and this the one at failure. What are these things here? The success of V. Do you remember that? What is that? To remind you that on-complete here is something that takes in a try and maps it to some value. Although I think in general it's unit, so it's actually not returning something. What is this? Why do I say case success of V? That's an example of what? Yeah. So it's a try. Both of these are tries. It's exactly right. And this is an example of what we call pattern matching in Scala. And we see that, remember, we saw it with matches and case statements. We saw it when we unpack things, return multiple arguments from a function. We've seen it in some other cases as well when we, for example, we have a loop in the book. I think there may be examples of where it uses pattern matching to take apart the elements returned from the loop. We saw it with regular expressions. So that's what that is, okay? And when we have case statements, the case statements provide us a nice way of doing this. What is this thing that I'm providing here? What's this between curlies? It's a function, but what sort of function? It gets with a P. Partial function. It handles these cases, which happen to be exhaustive. Collectively exhaustive and mutually exclusive. Okay, great. Okay, so that's a little feature that handles this operation. And it makes sense, right? Because a web access, this could take a good long time. I mean, maybe it's for some really slow website, you know, that's reached by a small pipe from where we are. Maybe we're executing this, you know, on a really slow connection. And it doesn't make sense for it to just wait there for most of the time. For many contexts, we fire that off, and whenever it's done, whether it's for a timeout or some other things, it will call off to this. We don't have to keep the current thread just blocked because of that. Okay, so that's an example of how we can use that. Let's continue on here, though. I'd like to now put into place something where there's going to be a very obvious delay, okay? And maybe what I'll do is put in place this one here. Val my future 3. And this will be a future of thread.sleep of 30,000, and then it's going to be and then semicolon and 5. Okay, what's the deal with the semicolon? I thought Scala didn't need semicolon. Some of you may be thinking, why is there a semicolon here? Why was there a semicolon here?
Multiple commands on the same line.
Yeah, multiple commands on the same line. If we had been able to separate this into separate lines, which you can easily do with doing the paste operation in the Scala shell, we wouldn't have needed that. But because here we've got these on the same line in this function, we do this. So what does this function return as a value? 5, but it's sleeping first. Okay, so here's my future 3. Okay, there we go. So with my future 3. I can say, hey, go map it to one more than itself, right? Or I could say map it and filter to see if it's greater than 3, right? And you'll notice that all of these are executing, even though this is not yet finished, right? Do you see that? Could say my future 3, you know, dot for each. Unfortunately, I'm running against borrowed time here. Okay, it's done now. It's good and done. Let me do that again just so you could see it for dramatic effect. I'm going to say I'm going to start this up, and then in addition to doing each of these, I'm going to do this, and I also did these maps here, right? It's just waiting for this, right? And you'll notice that this didn't block it. It's not blocking. It's asynchronous, right? This will get done at what time? When will this operation get done?
30 seconds.
Yeah, it will get done when the value is good and ready. When the value is ready, you could think of this almost like from an actor-based programming context. You could think of this as like a message that's been sent to the future saying, hey, when you're done computing, you know, undertake this. Oh, why is there a 5 there?
That's it, printing.
Yeah, that was its printing. Finally got around to doing this, right? Now we could leave ourselves in more suspense here. We could have this do, here, watch this. We'll have it do next string, length string 3, okay? Here we go. By the way, you notice that 5, I can't get rid of it. Why can't I get rid of, oh, no, I can't. Okay, mumble. Okay, well, a mumble. Okay, here we go. My future 4, and I'm going to say my future 4 dot, and I'll do the same thing for each, print this. Okay, there we are. We're just waiting for this, right? I'm going to frog various things, but what's going to happen when this is done? What's going to happen when it's done? When 30 seconds transpires. Bring
up 3 random characters.
Yeah, 3 random characters. I must confess that they're outside of my knowledge of Chinese. I don't think it says bo poo. In any case, that's the output from there, right? Okay. So it queued up, and you notice that the key point is this was awaiting. Whenever it got done, it would execute it. It's as if we sent it a message and say, hey, when you're done, do this. And whenever it happens to be done, it will go ahead and execute it. Okay. So we're not blocking. We're not waiting for it before we can do anything else. We can go on and do lots of other things like press D while this is happening, and etc. Okay. Let's continue on here. I would note that this filtering is also happening, the filtering and the mapping, etc. So all of those operations that we undertook before here are also happening. So if just to emphasize this, if I were to say future of this dot map, and I'll double the value, and I'll filter to see if it's less than 5. Okay. Oops. Oh, of course, I need that. Next, I'll say next int here. I'm going to say next int of 10. What's that going to give me? If I say next int of 10, what is it going to give me back? What is that going to give me back? Okay. Yeah, exactly. It's going to give an integer between 0 and 9 inclusive. It's not up to or not including 10. So if I did this, and if I were to then say for each print println underbar, okay, there we go. What do you think will happen?
And wait 30 seconds, and then it's gonna find out the result of that.
That's right. That's right. And so do you think it will always be an active result?
35% of the time.
So sometimes, yeah, sometimes it's actually going to be a value, and sometimes not. Sometimes there'll be nothing that survives the filter, right? Sometimes nothing will make it through that filter. Without waiting so long, we could of course change this to 10. And if you want to see it much more likely where it will actually pass, we could make it something, oh, sorry, much less likely. Okay, that's not so good. I'll switch it to that. There we go. And yeah, it's going to be highly likely that it will that'll be able to pass it. Yeah. Okay. So all these things got queued up for it to do when it's done, right? We could map it, we could filter it. What happens when we map a future? If we do future of 3. What happens when we map it to say multiply it times 2? What happens? What do we get out? A future. When we filter it to see if it's less than 5, what do we get out? We get out a future, right? This is just another promise, and we'll only execute at a later point. Okay. So I think you're getting some of the notions here. Now let's go a little bit richer. What I'd like to do to give us time to write it, I'm going to actually put in place this. I changed it, but I'm actually, to give us time to write it, I'm going to change it back. It's going to be this 7 times 10,000, okay? We're going to put in place this. So now we're going to be combining together several of these monads, okay? These monadic values, okay? Here we have 2 futures, and we're going to combine them together in a way that should look quite familiar to you, because we've seen it before, okay? So we're going to combine F1 and F2 to yield F3, okay? So these 2 lines are the same. You can ignore, there's, I don't know why there's a slightly different spacing, but, oh, except 1 is 2. 1 is 1 and 1 is 2. Okay, sorry. Cool. And then we're going to put this in place, okay? So where have we seen this pattern before? This pattern here? Anyone remember? We actually saw this several times previously. We had, okay, we want to combine 2 things, 2 monads. We have f1.flatMap, and then we're going to have f2.map. Why? Where do we see that? Do you remember seeing this for options? We also saw it for try. Okay, with try, it also, sorry? Yeah, exactly. This is sort of the sum as it's lifted to the future domain. We're adding together these 2 futures. Now, what if F1 is not something that is done yet? What's going to happen? Suppose F1 is not yet finished. What's going to happen when we invoke this? Yeah.
It's gonna wait.
There, it's gonna wait. It's gonna wait until it's done, and then it will go on and do this. What if F2 is not yet done when we get here? Well, it'll wait. It'll wait for F2.
Well, that execution context will wait, but we won't get hung up there, right?
We won't get hung up, right? It's just, again, it's as if we've sent a message saying, hey, when you're done with that, do this other thing. Do this other thing. We're not hung up just only being able to do that. So we'll get back, and we'll see this very, very strongly. I have the luxury of copying this. Maybe what I'll do is I'll go into paste mode, which is an extremely handy mode, I should know. And I'll do this. Oh, mumble. Okay. Sorry.
You close one print.
Oh, I need to close this for sleep, right? No. You know, they do these. Sorry, only the second one. Okay, sorry. Okay, I am after the number 7. Oh, there it is. Okay. Yes, thank you. Thank you. Okay. And we'll paste. Okay. So here's F3. It's not blocking. We can continue on and do things here. But F3 in the fullness of time is going to be of an actual value. Right now, it's just a promise, right? We could ask F is completed here, and it's going to say false, right? So it's not yet completed. Eventually, it will be completed. So we could say, again, F3 dot for each, print ln of this guy here, for example. And when F3 is completed, what's going to happen? What do you think is going to happen when F3 is done? Is F3 done yet? What do you think? Why does 3 suddenly appear there? Because that's its result. That's its result, which I would note is the sum of 1 and 2. So here we had this asynchronous operation. By the way, this is where Zeppelin really fails because it doesn't do this nice kind of updates to these things. But this was asynchronous. It was asynchronous. We were able to continue on, as Dorian said. It's not blocking. This flat map and the map in turn, those will be done when it's ready, but it's not sitting and waiting for them to be done. It can go on and do other things in the meantime and then execute. Okay. Simple concepts here, but turns out we can do it much more nicely using Scala's monadic for syntax. And for those familiar with other functional languages commonly have a similar syntax. Even Julia has a sort of do syntax. Similarly, Haskell has a do syntax. But basically, this is that same code written in a nicer way. Nicer because we're able to focus on the underlying values. It actually becomes much nicer yet if we're dealing with more values. But fundamentally, we're operating on the underlying values and adding them together, and it gets unpacked to this. This is just syntactic sugar for this, okay? It just turns it into flat map, flat map, flat map, and then an outer map. And then there's filtering going on with filter, I think it's called, which goes on without even creating a new collection. It just filters it in place. It knows which items pass the filter test. If there's an if statement, it's in here. So this is a monadic combination of these two in a way that takes advantage of the Scala syntax. Not particularly compelling here because there's so few of these, but if we started to have a lot more, we would see, okay, yeah, it's actually quite nice. Maybe if we were to, for example, if we had here 3, and I should take a copy of this, duplicate it so I don't screw up my original plan. If we had F3 and F4 here, we could do something like this. So we could have, Z gets, oh, come on, gets, and, X times Y, and we could in turn add in here, say, here, let's see, we could probably just do F3, times F4 or something like that. And this could yield X plus Y plus Z or something like that. In any case, this would be something where we can write in a very, very familiar syntax here, a more complicated thing. I'd have to make sure that that syntax works exactly, but we might have to grab F3 and F4 into variables. I think we do, actually. Sorry, folks.
Apparently your screen isn't visible on YouTube.
Are you serious?
Yes. Saying.
Oh, that's terrible. Okay, my apologies out there. Okay. Oh, that's horrible. When did that happen? I didn't mean for them to have to stare at my face. Okay, that's a horrible thing. Okay, sorry, folks out there. The indignity of staring at my mug for so long is bad enough. Okay, so we could do something like, you know, x times y plus z times w. There we go. Okay, happy. Wonder when that failed over. I've seen it happen in a few other cases. Okay, so what happened here? Where did I go wrong? Entered paste mode. Oh, of course. Yeah, probably I need to get all these things up here. Did I screw something else up though? Okay.
Or the first V.
First,
The first letter.
Well, very first value.
the B.
No, you don't have to change anything. You just
Yeah.
deselect it.
Oh. I mean all of this?
Yeah, you missed one character last time.
Oh, okay. Okay, there we go. No. Something else is illegal start of mumble. Here, let's so my hypothesis is the problem is up here. So that works happily. Let's go check these two. Okay. So that's very fine. Okay, let's go look at this separately. Fine. I wonder if there's something in between this that's okay. In any case, time is short. Okay, this is a longer example. This is actually from the Scala website, but basically here we're using the same sort of syntax. We're getting to quotes from web services for getting quotes regarding some currencies. We are here extracting the values associated with those futures, asking is it profitable, and if so, for those which are, then we'll buy some of the currency, and then we can call on success. So in the event that this is successful, you know, we'll report how much did we purchase. There's obviously a missing end paren there. So here we are operating on these underlying values. That's what this USD and the Swiss francs thing is indicating. And because we're using this special syntax, we can make use of sort of simpler representation than when we saw using successive flat maps, nested flat maps and maps. Okay, so where this goes at a very practical level is, you know, when we're dealing with very long latency operations, particularly long latency operations where we're not sure what's going to execute before what, and we're not sure, and we don't have many dependencies between them. We don't have to wait to start the next, we have to wait for the last. We can actually fire these up asynchronously. We can fire them up in a way that starts the operations before waiting for the previous one to finish. And there's a lot of operations that we work with in data science, which can have very long latencies associated with them. Some of them involve looking things up over the web, like was seen here, where we use a web service. Others might involve looking things up in a database. Other things, performing a computation. We're not sure how long it will take because it depends on the exact nature of the data in it. We have a set of operations that we want to do in parallel. it's very favorable to use these asynchronous mechanisms for that, these futures, to sort of allow us to express our computation in a way that just automatically handles when things are done, the required work gets done. So, common example here is waiting for user input. We say we wait for the user input for the search term. We're not sure how long the user will take. We don't want to wait for it. Then we perform a web search using the search terms. That's going to take some time. We don't want to just be waiting till our search engine comes back to us. That could be, half a second, 3/4 of a second. We might as well be doing other work. So handling that asynchronously is quite desirable rather than blocking. And then suppose we want to harvest content from the URLs. Okay, that can be done more or less directly without needing it to be done in a asynchronous fashion. But then maybe we want to perform an intensive sentiment analysis. We want to analyze the words to say, okay, what's the attitude towards the things being discussed? How emotional are they, et cetera? How positive or negative? And we want to perform the sentiment analysis on the contents from the URLs. Oh, I'm sorry. This content from the URLs, this is actually going and getting the web pages referred to in the URLs returned by the search. So that's actually very long latency. So this is, we're extracting the text of the web page of what was of the URLs returned by the search. So that's long. We don't want to wait for each one. We don't have to do one. We don't have to finish one. We don't have to finish the others. So they're really decoupled, and performing this in an asynchronous fashion is desirable. And then maybe we want to summarize the sentiment. In this case, we have to get all these done and then summarize them. So here, we can, for example, get these submitted search terms. This is actually, I wrote this in Java. I had meant to enable the Scala version of this, but this is fine. So here we'll get back, say, a computable future of a string from the user. And we'll compose it with doing a web search. We'll get back a computable future. You could think of just as just a future in Scala. And then we'll apply a extract links. We'll get back a list of URLs here. That can be done directly. And then in a parallel way, we will engage in reading the URL contents. We will perform sentiment analysis once we've gotten back the contents of the web page, of a given web page. And then having finished this parallel stream, this complete parallel stream, we're going to map the results here to get, and then take the average over them. Okay, so the idea here is that many of these places within the whole process can be undertaken in parallel. They can be undertaken in a fashion that doesn't need to block, the next one until the last one's done. Particularly with respect to this process of extracting, going and harvesting the contents from each of the URLs. Maybe we have, 1,000 URLs we've extracted from the web search. We don't want to be waiting to do the next, to start the next one going until the other ones are finished. So Scala, so in Java 8, this is supported with a computable future. In Scala, this is computed with with a future, like we've seen. Now, you just check the time here. Okay, now we're over time. Maybe I'll just note that we won't have time for some examples of this. In Spark, we make use of these futures, but we build atop of it specifically something called a future action. And a future action is a future. In fact, it's just a subtype of future, but it has some additional operations of note. I've listed two of the most important ones here, which are cancel and is canceled. So here, for example, if we were to go through this example more completely, which we, unfortunately don't have time to do here, we could For example, when we're going through these search terms, we'll harvest content from URLs for each of the pages returned. Maybe we find the content we're looking for. We find the content we're interested in. We don't have to go on and do the others. We've started the others. We've started them in a stream-based, in a asynchronous fashion as different futures, but in a different future actions. So we could then cancel it. Okay, we could then cancel those other ones because we don't need them anymore, and therefore spare a lot of computation. Okay. Now, there's a lot of things I haven't had time to talk about here. Some of the most key ones that we've only been able to hint at concern the this API more generally, and the fact that often we need to block at the end for a certain duration. We'll say, look, I need all of these to come together at the end to do my analysis. For example, to average these things together, I need to get the others at least resolved that they're a failure or a success. They either need to time out or they need to complete before I can average the sentiment scores across all of them. And one way we can do this in this framework is with this result method, where basically we'll call on a future and we'll say, hey, I'm willing to wait this duration for you to finish. And I can specify a timeout if I want to block for the result for me to then have the full set that are done. Alternatively, if we don't have to care about how long it's going to take, we're not concerned about timeout, we could call on complete or handle separately on success or on failure and handle the results. Okay? Okay, so that is unfortunately all we have time for today and all we have time for in the class for in-person sessions. I do want to record probably an additional session on use of SBT. I think that would be worthwhile, so you can see how to use that with Scala. And I may actually at some point record, the finish of this topics, which have to do with future actions and future in a richer example. But it's been my great pleasure to have you in this class. I look forward to working with you to see the projects completed over coming days, hopefully not months. And yeah, Christine will have my head if it's months. I know I've talked with you about many of the projects. I think everyone in here, I'm convinced, it's going to be a really interesting project, and I'm really looking forward to reviewing them. Okay, I appreciate you working with this course while it's sort of under construction and so on. I know there's been, parts which really need refinement, and I appreciate your patience with that. And I hope you've learned some useful skills and useful concepts when it comes to working with Spark and with Scala and with the ways in which functional programming can support systems which are scalable, robust, convenient to program, etc. Okay. So thanks very much. I'm available here for answering questions about projects. If you need to meet with me, between now and when your project's due, just let me know and I'll make that a top priority. Okay? Thanks very much.
Thank you.
All right.